So, welcome back to the HHH seminar. Apparently we're already on air, and so it's my pleasure to introduce Christian Schlichtkrull to talk about HHH quotient spectra.
Thank you very much, and thank you for giving me the chance to speak here. So I'm talking about a project in progress with Samik Basu. So my announced title was a little long, so instead of writing up the long title, I somehow explain you as you go along what it's about. So we start with R, which is an E-infinity ring spectrum. And to such a thing, we have the units here, one of R, which one can think of in various ways, but somehow I think of it as being the homotopy invertible element in the underlying infinity space of R. So that by definition it will then represent the unit in the zeroth cohomology group associated to R. Like that. Okay. So let me start by saying a few words about generalized Thom spectra. So that's going to be somehow an important part of the talk. So if we have a map F from a space X and into the classified space, then it has an associated Thom spectrum. Which I'm going to write T of F. And so here's a sketch construction of that, so one can do it in various ways. But let me just somehow sketch the construction as it was first written up by Ango and Getzner. Let's see, let me get it in alphabetical order. Bloomberg, Getzner, Hopkins, and rest. So we think of GL1 of R as a kind of a group like monoid, so it has a classifying space, GL1 of R, and it has a universal principal bundle over it, E GL1 of R. And then we can pull back this universal principal bundle to a principal GL1 of R bundle over X. And then we define this Thom spectrum to be the smash product smash over. So we can take the sphere spectrum generated by GL1 of R, so the spherical group ring, and that acts on R in a natural way, and we can take the derived smash product. So this is then by definition an R modular spectrum. So this is somehow the space level definition. So there's also a very slick infinity categorical formulation of what the Thom spectrum is. And I think somehow the fact that there are many good ways to write down this thing somehow suggests that one has found the right homotopy type that one should associate to such a map F. Okay, so the way to think about its homotopy groups is to think of them as they represent twisted R, say, so F twisted R homology of the space X. So something that most classical case when R is equal to the sphere spectrum, then TF is what one might call the classical Thom spectrum of the stable spherical vibration classified by F. And somehow even more classically, you would map first with X into BO, and then further on to PGL1 of S, and then you would get the really classical Thom spectrum. So another example is when we take R to be the Eisenberg-Lane spectrum, where A is a commutative ring. And in this case, BGL of R, well, that's simply the classifying space of units of A, and we can think of this here as being representing then what's it called, local homology. The coefficients in A, and let me give one more example. One more example which has been studied is the case of the complex K-theory spectrum, where in this case this Thom spectrum represents what is called twisted K-theory. So those twisted theory has been studied in some detail, and the notion of a Thom spectrum gives somehow unified way of thinking about them. So let's see. So it would be important for me to talk about the multiplicative structures of such a Thom spectrum. So multiplicative construction. I think that you can make a good multiplicative theory of Thom spectra in any of the models that you work with. But so here's a write-up by Basu and Bergen and myself, which somehow works with in a setting of diagram spectra. So we work with a model of the units here, which is an infinity space. And then we say that this Thom spectrum from spaces over PGL1 of R and into R modules in symmetric spectra, or we could also, it works the same in orthogonal spectra. So this preserves operate actions. So it takes an En space over PGL1 to a Thom spectrum with an action of an En operator. So actually what we really do in this paper is that we go one step further, so we work in a diagrammatic framework where we really represent the left-hand side as an honest symmetric monoidal category. Then we define the Thom spectrum functors as a really symmetric monoidal functor. So we are not dependent on any particular operator. But I don't really need to think about this technology now. Actually, what I really need is the following: that particular if f from x to PGL R is a movement, then Thom spectrum is an R algebra. So an R algebra in somehow the sense of being an infinity algebra or a strict symmetric ring spectrum, which is large. Okay. So we were writing about the multiplicative structure because, well, for several reasons, but one of them is that we wanted to generalize a theorem about topological Hochschild homology of such Thom spectra, which has previously been studied by myself together with Bloomberg and Cohen. We wanted to generalize this in the following way. And myself, and somehow it's fair to say that it's really based on the paper by Bloomberg, Cohen, and myself, in the sense that many of the techniques are quite similar. And somehow if we are in the situation there where we have a loop map such that the Thom spectrum TF is an R algebra, then we can look at the topological Hochschild homology. And this turns out again to be a Thom spectrum, although of a little strange map maybe. So this is a Thom spectrum of a certain map here, where the notation PF from Px to the looping of PGL 1 of R, but for this is a looping of F. So this is somehow what we have inside here. And what about this L eta? Well, L eta of PF, it's a map that starts at the free loop space of Px. And then first we use the looping LPF. And then we use that, here we have a multiplicative structure on the second looping of GL1 of R, so infinite loop space in fact. So we can split this as B2 of GL1 of R times GL1 of R. And then we can, so now the eta comes, so I say that there is a map which is eta on the first component and the identity on the second component. And then we can multiply together. So this eta here, well, if you think of the spectrum associated to GL1 of R, then you can smash this spectrum with the stable Hopf map, and this is then what you get somehow on this basis of the spectrum. You get a map from the second looping to the first looping of GL1. So it's a map which maps into PGL1 of R, so we are entitled to construct this Thom spectrum, and that's somehow what it is. So it's an equivalence of R module spectrum.
Am I missing a B someplace?
Excuse me?
In the equivalence on the loop space.
Oh, there's a B missing. Otherwise, the identity would not fit naturally in the picture. So there's another way to write off what this map is, and that is to think of the free loop space here as being the cyclic bar construction of X, which X has a multiplicative structure. And we could map the cyclic bar construction of X to the cyclic bar construction of PGL1 of R, which also has a multiplicative structure. Well, this is actually an infinity space, so here we are allowed to multiply the elements together in each degree to end up in PGL1 of R. So we couldn't do that for X, which is only a priori a single loop space. And that would be an equivalent. So that map is somehow equivalent to that one. And the way that eta turns up is that the map from the cyclic bar construction of an infinite loop space down to the infinite loop space, this map is not somehow compatible in the picture using the free loop spaces with a section that takes bx and maps it into the free loop. That's somehow a funny, that's a funny fact which gives this description. Okay. So the next thing that I'm going to talk about is the quotient spectra. And it comes as a theorem. It is actually from the same paper as I mentioned before. And it says the following. So now we should assume that R is an even infinity ring spectrum. So even means that all the homotopy groups in odd degrees are 0. And suppose that we are given some classes in the homotopy groups of R for I equal to 1 up to some n. Then there exists a loop map f from SU n plus 1, so n 1 more than the number of variables, to VGL 1 of R. This is the loop map such that Thom spectrum of this map F is equivalent to what somehow is sometimes written R modulo 1 up to x n. So, if we are giving a sequence of the classes in the homotopy group, we can inductively construct such a quotient here by somehow as iterated homotopy cofibers of multiplication. This is somehow the homotopy invariant meaning I give to this one. And one thing that comes out of this theorem here, but first of all, it shows that such quotients here occur as Thom spectrum. So, for example, R could be complex K-theory, and you could have like just one variable, x1 could be p times the point element, something like that, and then ku mod b would be the Thom spectrum, and actually it would be the Thom spectrum of a loop map, so that would show that it has an R algebra structure. So there are some things that are not exactly the same working with ring spectra as it is for working with ordinary rings. So both are objects, both are monoids in a symmetric monoidal category, and somehow many formal things are the same, but one thing that is quite different is the thing of taking quotient spectrum. So if you have an ordinary commutative ring and you have an ideal, well, the quotient is just a ring. But it's not so easy for ring spectra, and even in cases where you still get the structure of a ring, it may actually have different ring structure, and it may be complicated to keep track of those different ring structures. That's somehow part of what I'm going to talk about. Yes?
Which stage of this equivalence needs xi to be in even degrees? Can you construct the T of f for any xi's, or do you need it to be even for the T of f?
But this one you can construct it for any x's. This is somehow another way to say what this is that you form the x mod x I and smash them together. This one you can construct it for any loop map, but the statement that is depending on having these classes in this degrees is that we can realize this quotient as a Thom spectrum. And I'm going to give you a sketch of the argument so you see why that shows up. So let me give you a sketch of the argument. Well, first of all, since we assume that R is even, then it's complex orientable. That implies, among many other things, that we know that what the value of the complex projective space is, it's the pi star of R with a generator C, and then mod C to the n plus 1. But we say that C sits in homology degree 2. Okay, so now we can use these classes here, x1 times c plus x2 times c squared plus xn times cn. We can think of this as being an element in the unit of CPN, so that it gives, let's call it U. This element, so it gives a map U by what I started by saying it then gives a map from CPN and to GL1 of R. Okay. Now there's a good map from the suspension of CPN to SU n plus 1, kind of a complex reflection map. And since well, so we have a good map here into BGL1 of R, and we would like to somehow define our map to be an extension of this diagram. But actually, we want to be even more ambitious. We want this to be a loop map. So actually, we just go on with it. Write it off once more. So we just suspend once more into U1 of R. And now down in B is U n plus 1. And here is my delooping B. And now we need to use that R is even to say that there are no obstructions to this extension. And that's somehow, this is just, one just looks at the obstruction groups and there are nothing there. So we have an extension. But of course, the fact that there is an extension does not tell us that there's only one. So a priori there can be many different extensions, and that's actually happening. So that will be somehow that will be apparent from the calculations. Let me maybe give one more remark here, which will also be relevant. If R is 2 periodic, which I'm going to assume for some of the result periodic, then the dimension requirement on xi is superfluous. How do you spell that? Okay. Because then we are free. If we have a unit in degree 2, we are free to move these classes up so that if we're giving classes in any even dimension, we can move them to sit in the right dimensions, and then the quotient somehow will be equivalent under this chain of error. Okay. So the theorem that I want to discuss then, so first there's a corollary. If we combine the things that we have so far, it then says that the topological Hochschild homology of such a quotient spectrum.
So what? I mean, once you've got the map, we're just supposed to apply the theorem to get the.
Yeah. Well, so I have not explained really why this map, why the Thom spectrum of this map is the quotient spectrum. So that's where the sketch comes in. So it's not. So there's an argument needed. Yes.
Do you want to say anything about it? No.
No, because then I would not. No. because I wanted to talk about a newer result. So this is already published. So what the corollary then is that this is HHH of this thing is then the equivalent to a Thom spectrum of this this map here from the free loop space of BSUN plus 1 into BTA. So to calculate the topological Hochschild model of the quotient spectrum, we need to calculate the twisted homology of the free loop space of BSUN plus 1 by this somehow eta twisting.
So is the ground ring in this corollary R or is this S?
Yes, I'm sorry, this should be R. Thank you. I don't know if I said that, but I should have said that that the based on Bloomberg-Cohen is the case where R is equal to S. So there we work that out. Okay. So the new theorem that I want to talk about is the new theorem is somehow related to this fact that there can be several different multiplicative structures on a quotient spectrum. And how can we measure that? Well, we could try to understand the moduli space of all multiplicative structures, which would be somehow a very ambitious goal, maybe. So I have something. Right. So I calculate the topological Hochschild model and see that I get different groups. So the multiplicative structure has to be different. So here's the theorem with Basu and myself, and that's which we are writing up now. So we have P as a prime, and R is a P local even to periodic infinity ring spectrum. So we make quite a lot of assumptions on R in order to be able to make this calculation. So then let's suppose that we have elements in the homotopy groups of R that actually form a regular sequence. Since I now assume that R is too periodic, I'm not longer worried about which particular resource elements are fitting. Then I say that for each k greater than or equal to 1, such that, so there's a limit to how big it can be, so we should have n plus 1 times k plus 1 plus 1 should be less than or equal to p. There exists an R algebra structure on this quotient spectrum such that when we calculate the homotopy groups of HHH of it, it becomes isomorphic to a direct sum with k copies. So here's k of somehow a big R module where, so this big R module is defined somehow, is somehow what you get by making all these elements divisible. So defined as a colimit of those truncated polynomial rings, no, not truncated polynomial rings, those quotient rings here, J1 up to xn Jn, where the colimit runs over J1 up to Jn.
Sorry, so is there some homotopy group somewhere missing in the right hand side?
Oh, yeah. So then we take the homotopy group of R and then we mod out by these classes here. I forgot that in my notes. Okay, so that certainly says that there are some different R algebra structures on this spectra here, and we can somehow give a rough idea of somehow identifying some. So this list is not supposed to be exhaustive. I think it's more one should think of it as being a way of identifying some multiplicative structures such that the algebra here for the topological Hochschild homology gets a rather somehow understandable description. So one can somehow, maybe that will be clear when I somehow talk about the construction, that I think that one can define many multiplicative structures such as a quotient, which will make the homotopy groups very, very complicated to describe. Right. So we have this corollary here, which says that asking about the HHH of the quotient spectrum is equivalent to asking about the twisted homology of a free loop space. So one would think that we have a lot of machinery somehow in homotopical algebra to discuss such a homological algebra construction, so why don't we use some of that? But in fact, it turns out that our in this particular paper, we actually work on the right-hand side and try to analyze the twisted homology of free loop spaces. So let me explain how that goes. So then we'll also recall some classical facts about free loop space and the relation to the cyclic bar construction. So what we're actually going to look at is a semi-simplicial model of the free loop space. So there will be a semi-simplicial model of that, and then there will be a Siegel times spectral sequence which calculate the homotopy groups of the associated Thom spectrum. So how does it work? Well, so this free loop space is equivalent, not homomorphic, but is homotopy equivalent to the cyclic bar construction of the group SUN plus 1. This is somehow a classical fact which is true for any group. And this cyclic bar construction is actually homeomorphic to the homotopy orbits of SUN plus 1 acting on itself by conjugation. There's a lots of n plus 1s here, but if I didn't write n plus 1 some places, I would have to write n minus 1 some other places. So I'm a positive one. Put some plus in. So this is actually, since we have an honest group here, I'm very happy for this example, since usually I'm not somehow so lucky that things are really grouped, but here we actually do have an honest homomorphism, so it does make sense to talk about the conjugacy action here, and we can form this homotopy. Okay, And I want to define a certain semi-simplicity structure on that thing. And what I use is that we know what the space of conjugacy classes is. So, the maximal torus in SUN plus 1 is, well, no. So it's a copy of elements in the circle such that the product of the set I is equal to 1. And then I will think of this as a diagonal matrix sitting inside SUN plus 1. So it's an n torus sitting inside SUN plus 1. And we have a homomorphism which describes the space of conjugate classes from n simplex to the maximal torus divided by the action of the y group, which would be sigma n plus 1, and then SU n plus 1, C modulo, and here I mean the total space under the action by conjugation. And they are all homeomorphic, such that actually the homotopy type is that of an n simplex. And if you're good at Lie theory, this is all somehow very classical. And in this way, one can write it up explicitly, so I'm going to do that. So what I want to say is this is general Lie theory, but in this case, one can actually write it up very explicitly. So I use another model of the n simplex given by coordinates t0 up to tn in n plus 1, such that they lie on a hyperplane t0 plus up to tn is equal to 0. And then there are some inequalities. t0 is less than equal to t1, less than equal to tn, less than equal to t0 plus 1. And this we can map into maximal torus simply just by doing the obvious thing. So t0 to tn is mapped to the diagonal matrix with entries e to the I to pi t0 up to e to the I to pi tn. Okay. Now I want to use the structure of the simplex to get a semi-simplicity structure on the homotopy vortex. Details of that. So let's call the vertices of this simplex something. Let's call it V0 up to Vn. Then if we are giving a phase here, or a k phase, then has the form Vi0 up to Vik. We have the following that. See, there are two things that holds. First of all, the centralizer. Let me write this as capital Sept of this diagonal matrix, so this one that I wrote up before. This thing here is constant on the interior of such a simplex. That's simply because it's a diagonal matrix, so the centralizer just depends on how many distinct eigenvalues there are, and they are somehow constant in the interior. And the second thing is that if we have a point on the boundary, that's actually on the boundary of this phase, Okay, now actually I want to give a name to this one. So call this centralizer H of I0 up to Ik. So for each phase we have a specific group, subgroup of the spectral unitary. And what I'm saying here is that if you have something which lies on the boundary, that means that there are more equalities, so there are fewer eigenvalues. So actually this centralizer here is contained in the centralizer of the corresponding element. 0 up to E by 2 pi T. So the centralizer becomes bigger somehow on the boundary, and this will be relevant if well, that will be relevant for the definition. Semi-simplicial space x n plus 1, which is going to be the one that gives us this Borel construction. So I say that in the decay we maps to the disjoint union over all the phases, or decay phases of SU n plus 1. And then, well, so I take the homotopy orbit then of SU n plus 1 and then divide it by this subgroup here, H of I0 I k. So the simplicial structure, or the semi-simplicial structure map, they now come from, if I delete one of the vertices, then I have a projection map. So if I delete one of the vertices, then the centralizer here becomes larger, so I have a projection map going down. It gives a semi-simplicial space such that now the topological realization of that is homomorphic to those homotopy orbits that I'm after. And I'm going to use that to set up a spectral sequence. So let me do that in the next tutorial. It's very classical that there is a spectral sequence for a semi-simplicial space and an arbitrary homology theory. Construction, I think, was written first up by Siegel, and we are just going to consider a variation of that. Let me formulate it as a theorem, maybe, which says that if we are giving a map, I just call BF from BSU n plus 1 and then to B2 TL1 of R. Then there is a spectral sequence with E2 term equal to HP of so I still have my ring spectrum R around. Let's see. And I want so the spectral sequence actually works for in general for a semi-simplicial space, but let's just consider the one that I wrote up here, where I fix the n somehow to remind me that I look at SU n plus 1, and then a boundary map DI BF, which let's see to get the parentheses which then converges to the homotopy groups of the Thom spectrum of this map that I'm interested in, this twisted homology of the field space. So I should, what are then the boundary maps? So here, this DI F, it's a map from RQ of XP of n plus 1 to RQ of XP of n plus 1. So here, what's happening in the first stage is that I multiply by a certain unit, so I take the cat product with a certain unit, which I call U P, I. So where P is for the semi-simplicity degree and I is for the operator. And then I use the semi-simplicity structure of X, which on the was called DI. So what is this unit here? Well, where I'm not going to describe that in detail. So where UI, UP, I is a certain unit in the cohomology of the space xn plus 1 and is determined by this map BF. It's yes. So it's necessary that there's something happening, because if there were no unit here, then it just would be this sequence spectrum sequence, which would calculate the R homology of the free loop space. And since, well, in general, the Thom space construction has a different homology, there must be something that somehow accounts for that, and that's exactly that we multiply by this unit. I'll show you an example at the end which show how that works. Right. So the theorem is gone, but from the board. But remember, there was a condition on the K, and there was a condition on how many copies I could have of this big of the divisible module. And that, so let me explain where that came from. So I can just fit that in here, I think. So what we are trying in this project is somehow to see how far can we get without knowing too much about the units of a ring spectrum. The units are fairly, I don't think that in general one has a good understanding of the units of a ring spectrum. In some special cases it has, but in general I don't think so. So what can we say in general about HHH, just knowing that R is P local? And if we know that R is P local, then the Case-Postnikov section, this decomposes as a wedge of Heisenberg-MacLane spectra for K less than 2p minus 4, I think it is. Since this is the case, we can control the units UP, I in a number of degrees. So the calculations that we do are, for a big part, it's cohomology calculations. So we are dependent on the fact that somehow we know that we can represent certain maps into BGL1 of R by knowing that a certain certain particle section of that splits into Einbremer lane spectrum, so we can calculate. So it's sufficient to know what the homology groups are in order to define this map. So let me try to spell that out in an example. I think I have time for that. So I'll just do the simplest example. So the bookkeeping does become somehow a little bit involved. I should say one thing also, which I forgot to say. I should say that the Glad amplifier has been doing some results along these lines, using completely different techniques, and also getting so this result about existence of R algebra structures, at least somehow for k equal to 1, that was in an early paper I could find already. Okay, let's see. The second example, where we should say k equal to 1. So the situation is that we have an element in P. Well, it doesn't really have to be in pi 2, since I suppose R is periodic. It must just say that it is in pi 2 of R. Then I have a map from SU2 into BGL1 of R, such that the Thom spectrum of F is this quotient spectrum here, and I want to look at the topological Hochschild homology. So R could be, again, complex K theory, and A could be P times the odd element, to think of something concrete, and I somehow would like to understand HHH of that. Okay, so what does the spectral sequence look like? Well, X0, 2, so 2 is for, let's see, I wrote 2 here, but I think in my, no, X2, I think I had n plus 1, let's check it. Yes, it was n plus 1, so, and you can, this is still, no, it's gone, but so I just write up what it is. So it should be, well, we should take the vertices in our simplex, and we should take the centralizers, and there are 2 vertices since it's a one-dimensional simplex, so it gives us 2 centralizers, vertex 0 and 1. And in this case, well, it's actually a scalar matrix, so the 2 diagonal entries are equal, so the centralizer is all of it, so PSU 2 and unique PSU 2, which is HP infinity system union HP infinity. And so there are only 2, there's only x0 and x1 here. So for x1 we should take the whole simplex and the centralizer of the whole simplex. Well, for the whole simplex we have 2 different eigenvalues. So here it's just the maximal torus that centralizes that. So the maximal torus in this case is just a circle. So it's p of x1, so it's CP. So let's give a name from the map, the canonical map. I'm not so good at HP infinity. I don't work so much with that, I guess. Map. Then we can write up what the spectral sequence is. So we have R star of B of HP infinity starts from R star of HP infinity. That's my zeros column. And I have my first column, so that's just R star of CP infinity. This is my first column. and the way that this unit works out, so let me just write this up. So the first coordinate here uses this canonical map composed with a unit determined by a choice of delooping, and the other one, in order to, in general, there will be a sign to make it differential, so it's minus pi star. So those groups are of course known. So let's see, for some unit u in R0 of Cp infinity, which is polynomial power series ring, I guess. This here, so in degree. So we take this power series degree and then we loop into degree 0, and u is some unit, some power series, which is determined by the looping of this map. Okay, so let's see, I have 5 minutes, I think. So we know what these groups are. So R star of hp infinity is the module of generators v0, v1, so on, where I guess it's maybe a new I for I, and I star of infinity is, see, I'm somehow changing notation here, it will be consistent. It's I star of R on some classes which are called beta, where beta I has to be 2I, and the map pi star of beta to I is equal to nu I, and pi star of beta to I plus 1 is equal to 0. Okay. So the point is now that in general, if we put in a unit here and try to calculate that, will be somehow a complicated program. Well, it's not. Yeah. So we want to use the fact that P is that R is P local to be able to choose this U here such that we can actually control what the co-kernel becomes. And let me just say how that works in an example. So for P greater than equal to 5, we may choose the left here from so this is looping from EHU2 to EG1R such that the unit is 1 plus A times C. So I have to put an A here in order to get the Thom spectrum. This is somehow part of the explanation why I get the Thom spectrum. But then I can skip the C squared term and put a mu cubed plus C to the cube plus higher terms, where this mu the degree 2 of R is a unit. So let's just see how it works out in this case, and then so I have no control on what the higher terms of this unit may be, but it's not needed to say what the co-kernel becomes. So in this case, I can then calculate. Actually, there's a 2 here if you want to. No, it's not important. Okay, then pi star of, I'm going to take the cat product of the even dimensional classes. I just, turns out that I get mu I mod the classes from 0 to I minus 2. But when I get it for, when I take the cat product with an odd dimensional class, I get this A times Vi plus 2 mu cubed v I minus 1, now my mu 0 up to mu I minus 2. So if you look at that and look at the co-kernel, that means that we now have a relation between A times vi and vi minus 1. So 2 is a unit here, so when we do that for all i's, so you see the first relation here together with, so remember we had a minus I star in the second coordinate, I star, that shows that we can disregard one of those factors here. So there's just one of them left, and in this one we build up these relations here, so that shows that the co-kernel is in I star of R mod A infinity. And if I now had a p that was bigger than 7, then I could make a bigger gap here. I could take the next one to be 5. If I had a bigger gap here, then I could make sure that I would only have relations between even classes here, and that would mean that I would get 2 copies of that divisible, and so on, so on. So the bigger, the more control I have of this power series, the more direct summers of this sort. Okay, that's all I had to say.
Questions?
So this method shows us that we have lots of multiplicative structures on these quotients for like big P and stuff.
Yeah, BP.
No, for big P. For P primes that are large.
Yes, well.
Do we know about what happens when primes
I
are
guess it's.
small?
I guess that we can write some up where somehow we have some kind of control over for BP.
Yeah.
Let me say like that. But there are probably lots that we don't have control over also for.
So do we know for like P equals 2, do we know multiple things?
In some cases we do. So we do know something about, for example, the KU. We know something about KU mod P, for example. This has been studied, and one knows about different multiplicative structures there. But for in general, if you take somehow MU and divide by some classes, I don't think that we know a lot about the multiplicative structures. Or I don't. Yes?
So if I take E theory, right? And or about A theory?
Yeah.
The 2 periodic one?
Yeah.
So I think that, right, I mean, so big life proves that the THH relative to EN is the same as the one relative to the sphere.
Let's see, there are different versions of that.
For the
Let's
periodic
see.
one. But I also thought that he proves that Moravec A theory has a unique structure. It's an infinity algebra over the sphere, at least for the 2p to the n minus 2 periodic version. So is really the subtlety coming from the fact that you take 2 periodic instead of like a higher periodic one?
Yes, I think so. Right. I think that you have the unique in this. Yeah, I think that's.
So you get more than one A infinity structure over the sphere on this 2 periodic Moravec theory for large primes.
For the sphere, I suppose so. Yes, I think so. Let's see. Wait a minute. So when is it that he knows that it's the same for the? So what Toby is saying that sometimes. Well, I should have looked at this paper more recently.
Yeah, I just looked it up right now because I was also confused.
Okay. So Beeline has some nice results that compares those two here when we plug in a certain periodic Moravec-Casey they compare. And I think it's somehow with the higher, isn't it, with the higher period, those two are equivalent, or am I remembering wrong?
So, yeah, I think he proves it both for the completed Johnson-Wilson and the quotient of that, and for the 2 periodic Moravec theory and the quotient of that, which is the thing that you were using. And both the homological and homological version.
Yeah, but Right, yeah, well, then you get them different.
First one, so the unit U is somehow canonically associated to F as a loop map? Could you say how to get it?
Yes, I can say something about that. So, so in general, if you have a semi-simplicial space, I think it's easier to actually discuss in general. If you have a semi-simplicial space X mapping into BGL 1 of R, and then if you assume that this map here is non-homotopic, that means that when you map xp times delta p in here, and then look at two of the vertices here, well, if you look at the two vertices, then you need to keep track of non-homotopic and so on, but you have a non-homotopic for those two ends. So then you can look at paths between those two vertices, and that gives you a loop in BGL 1 of R, and therefore an element in the units.
Mhm.
And right. So this is, and then somehow we look at this in this particular. There's a bit of geometry going into to see what those units actually are for this. In this case here.
I think we should have a discussion over coffee.